All right. So again, we are continuing what we did in the last chapter. We are describing motion. Okay. And this subject is called kinematics. Okay. And now, in the last chapter, what we had done was we described the motion of an object in one dimension. Okay, so an object went back and forth along a straight line, and we described that motion. And what did we learn? Do you guys remember what is the best way to describe a motion like that? What is the best way to describe motion, or at least the way we care to describe the motion? Here is how you describe a motion. You give its position as a function of time. Okay. Now we'll generalize this to 2 and 3 dimensions. Okay. So these are more realistic motions, or that you encounter more often. Okay. And you always give the position of a particle with reference to a coordinate system like this. Okay. So if the motion is in 3 dimensions, you draw an origin someplace. Okay, so let's say you get on a plane and you go on a flight. Okay, so your origin can be the airport and whatnot. Okay, so here's the x-axis, y-axis, z-axis. What we are interested in is describing this motion. Okay, so let's say right now that's where you're located, and your position vector is this vector. It's a vector drawn from the origin to where you're located. Okay? This is r, denoted by r, and this gives you your location at time t. Okay? A little while later, you might be there, and your position vector would be that. Okay? Now, how do you describe this motion? Okay, what you do is and the best way to describe this motion, the way that's most useful to us is RT is XTI. Give me the x coordinate as a function of time plus the y coordinate as a function of time and the z coordinate as a function of time. Okay. So here is a 3-dimensional motion. If somebody gives you these 3 functions, they've described that 3-dimensional motion. Okay, if the motion occurs in 2 dimensions, so for instance, if you're not flying and you're driving, then all you need is these 2 functions. Okay. All right. So I will give you the punchline of the chapter. I'll give you a function RT. Yes. Actually, all right, so here's a motion that is described to you, okay? And what this is actually a spiral motion, an object spiraling upward, okay? So what will be is, so here's a complete description of the motion. If you're giving the x coordinate as a function of time, the y coordinate as a function of time, and the z coordinate as a function of time, you've completely described the motion, okay? And the 2 things that you're interested in calculating is the velocity of the object at any given time What is happening?
Oh, I was just on the first one second.
Is it blinking?
No.
First one, that's cosine, right?
Yeah, that's cosine. 5 cosine 7t plus I mean 7 cosine ti plus, yeah. Okay. So what we are interested in is Vt, which is the time derivative of the position with respect to time derivative of position, okay? And so this would be d by dt of, okay, this is xt, this is yt, okay, so I'm going to all right, you guys understanding this? All right. Okay, so what is the time derivative of this? Very good. So derivative of cosine is sine and a negative sign, and you get a 7 from here, so it's negative 35 sine 70 I. What is d, the derivative of sine? Cosine, so plus 35 cosine 70 j, and plus, what is the derivative of this? 9. Okay, so 9k. So this is the velocity of the object as a function of time. Okay, so you can see that the velocity, the z component of the velocity is constant. Okay, so here's an object that is spiraling upward, and the z component of the velocity is constant. All right.
I have a question. How are you taking the derivative? Because if you're taking this with calculus, we're not there yet.
All right, so you're getting a preview of that here. Either that, or what you can do is you can drop the class, get your Calculus 1 now, and take the Physics 1 next semester. And so, and the other thing we're interested in is the acceleration of the object, which is dv by dt. Yep. So you take the, so, and dv by dt, by the way, this is the x component of the acceleration velocity, this is the y component of the velocity, this is the z component of the velocity. Okay, so this would be d vxt by dt. All right, I hope you guys are understanding the notation. Okay, this is the x component of the velocity as a function of time. Okay, plus dvy all right. Okay, who wants to help me out with the derivatives? I'm sorry? So this is 7 times 30 is 210, 245, okay? So negative 245 cosine 70i, negative 245 sine 70j plus 0k. All right, so the acceleration is in the xy plane. There's no acceleration in the z direction. Okay, so so that's what these are the things we're interested in. Okay, so what we'll do is, let me do this. All right, so I'll draw a picture of this. So. All right, so here's the position of the object as a function of time. Okay, at t equal to 0, actually what I'll do is I'm going to erase this guy. Okay, so the velocity won't change and that won't change. So here's the position of the object as a function of time. At t equal to 0, it's at 5 units. The x coordinate is 5 units. The y coordinate is 0 units. And at t equal to 0, the z coordinate is 0 units. Okay? The velocity is given by that. Okay. The radius of this circle is 5 units. Okay. Again, don't worry about it if you don't understand all the details. I'm just showing you. So the trajectory, here's what it's doing. So 1, 2, 3, 4, 5. Okay. So here's the trajectory. There's how the object is going. Okay, that's the trajectory. It's going at 9 meters per second in that direction. Okay. And so here's the position as a function of time. Here's the velocity as a function of time. Okay. And you'll learn that the velocity at any instant is tangent to the path. Okay. And oops. And here's the acceleration. Here's the acceleration as a function of time. Okay. And you see this acceleration is in the xy plane. You will learn that when an object goes in a circular path, the acceleration is pointing towards the center. This is the centripetal acceleration. Okay? And the magnitude of this acceleration is, see, that's the magnitude of this acceleration, 245 meters per second squared. All right, so again, to summarize what's going on, to describe any general motion, what is it that we need? You need to give me this function. Once you have that description, you can calculate the velocity of the object, which is dr by dt. And you're interested in the acceleration of the object. Okay. The acceleration is dv by dt, which is equal to d square r by dt square. All right, why are we interested in all of this? So for instance, okay. If you're Elon Musk and you want to shoot a rocket and you want the rocket to go like that, Okay, so if this is what you want, then you can calculate the acceleration you need and the thrust your rocket needs to have. Okay, so that's what we are about. Yeah. Do you guys have any questions? Do you understand this? All right. So all we're doing is now we're doing three-dimensional motion, so you need three functions to specify the location of the particle, and you can calculate the velocity using this formula and the acceleration of the particle using this formula. Okay. All right. So let's look at this. Let's go over the slides. So we'll define all these terms. Okay. All right, so here is the position of an object. You give the position of a particle with respect to a coordinate system. Okay. And we always use a right-handed coordinate system. Okay. The right-handed coordinate system is like so. Here's the x-axis, here's the y-axis. If you turn a screw from the x to the y-axis, if you turn the screw this way, the screw would move in that direction, in the z direction. Okay? So that's a right-handed coordinate system. A left-handed coordinate system would be if you move the screw from here to there, the left-handed screw would move downwards. Okay? Now you can describe everything using a right-handed coordinate system or a left-handed coordinate system. Okay? You just have to agree to be consistent. And for the past 200 years, all scientists in the world are using right-handed coordinate systems. Okay, so we'll stick with that. Yeah. So here's a right-handed coordinate system. There's the location of the particle, and as this moves, what you want is its x, y, and z coordinate as a function of time. Okay. So for instance, here is a motion. Yep. And a description of that motion is best given in terms of these three functions. Okay. Now we'll define a displacement vector. Okay, so if the particle is here at time t1 and here at time t2, okay, the displacement is a vector pointing from the initial point to the final point. Okay. Just like in 2 dimensions, we said that if you go for a walk, here's the initial point, there's the final point. The displacement vector is just that vector. Okay. So that's the displacement vector. Okay. And in coordinates, it would be the x coordinate at time t2 minus x coordinate at time t1 and so on. The average velocity is a vector, is the displacement vector divided by time. This is a scalar, so vector divided by scalar is a vector. Okay. So which way is so here's the displacement vector. What is the direction of the average velocity? I'm sorry? Okay, so you guys know this. Here's a vector A. What is the direction of 3A? In the same direction as A. It's just 3 times as long. The direction of this vector is in the same direction as this vector, except that the length is different, that's all. Okay? And the units are different. So the average velocity vector is also pointing in that direction, in the same direction as the displacement vector. Okay, what you're really interested in is, generally you're not interested in average velocity, you're calculus expert, so what you're interested in is instantaneous velocity. The limit of this in the limit delta t going to 0. Okay. And in the limit delta t going to 0, here's the average velocity in the limit delta t, that's the derivative. And that's the instantaneous velocity. Okay. and the instantaneous velocity is tangent to your trajectory. Okay. So here your instantaneous velocity is there, pointing in that direction, and so on. How fast are you going at any location? Instantaneous speed. So it's the magnitude of that velocity vector. Okay. So going back to this example, how fast are you going at any given instant? It's just the magnitude of this vector. Okay. All right, so the instantaneous velocity is that. So the velocity is Vx, that's the, so it's the x component of the velocity plus the y component of the velocity plus the z component of the velocity, which is equal to dx by dt I plus okay, so this is the x component of the velocity, this is the y component of the velocity, this is the z component of the velocity. Again, dx, again. The magnitude of the instantaneous velocity is your instantaneous speed. Okay. So, just to give you an example, you guys know how to calculate the magnitude of a velocity. Here's the velocity as a function of time. Here's the x component of the velocity, y component of the velocity, z component of the velocity. The instantaneous speed would be vx squared plus vy squared plus vz squared. Okay. Which would be minus 35 sine 70 square plus okay, so there is your instantaneous speed as a function of time. All right, so for this particular case, see that plus that square is 35 square and plus 9 square. Your instantaneous speed is constant. Your speed is constant for that motion. So the other quantity we are interested in is acceleration. Okay. So you describe a motion, you give the position as a function of time, you're interested in its instantaneous velocity and the instantaneous acceleration. Okay? So let's start off by defining average acceleration. Average acceleration is change in velocity divided by the time over which that change happens. Again, this is a velocity vector. This is a vector divided by a scalar is a vector. Okay? The dimensions of this are length over time divided by time. So acceleration has dimensions of length over time squared. Yep. So let's say if you were traveling along this path, this is your velocity now, this is your velocity a little later. The change in velocity is this velocity. So change in any quantity is the value of that quantity at the final time minus the quantity at an initial time. Okay? So change in your bank balance, for instance, is what your bank balance will be tomorrow minus what your bank balance is today. Okay? so again, how do you get the difference? Okay, so when you draw the two vectors, okay, so when you, here's the initial velocity, here's the final velocity drawn from the same point, the change is pointing from the initial velocity to the final velocity. Okay, so when you draw the vectors from the same point, it points from the initial velocity to the final velocity. Okay, here's another way to look at it. So change in velocity vector is v final minus v initial. So v final is v, I'm going to bring this over that side, v initial plus delta v. Okay, and there's this vector, so this is v initial, no, so this is right, so okay, so this is showing you this equation, v final, and here is negative of v initial equal to change in delta v. Okay, here's a better diagram. Okay, so here's a better diagram. So delta r is r2 minus r1. So r2 is r1 plus delta r. Okay, so the final value of the vector is equal to the initial value of the vector plus the change in that vector. The final value of the vector is the initial value of the vector plus the change in vector. It gives you the final value of the vector. Okay. All right, so here is acceleration. Acceleration is change in velocity divided by the time over which that change happens. Okay, if your velocity is not changing, what is the acceleration? Zero. If your velocity is not changing, this is the zero vector divided by the time over which that happens, is your acceleration is zero. Okay. You are interested in instantaneous acceleration. What does that mean? What is the acceleration at this instant? Okay. And that's the time derivative of the velocity vector. So your instantaneous acceleration is your average acceleration in the limit delta t going to zero, which is dv by dt. Okay. So dvx by dt is the x component of the acceleration. dv by y by dt, the time derivative of the y component of the velocity, is y component of the acceleration. dvz by dt is the z component of the acceleration. Okay. All right, so I'm going to remind you of a couple of things that we've talked about before, and then we'll try and apply it to a general trajectory. Okay. Okay, so in this case, are you accelerating? Is this particle accelerating? Yes. Okay, what is happening to the velocity? I'm sorry? The magnitude of the velocity is increasing. The direction of the velocity is not changing. Okay, so in this case, the acceleration was tangent to the path. Okay, so we'll consider a different case. So now let's say you're going on a circular path at constant speed. So What does constant speed mean? I'm sorry?
No net acceleration?
No. I'm sorry? Very good. The magnitude of the velocity is constant. And you can see that obviously the direction is changing. You're accelerating anytime your velocity changes. Okay? So your velocity can change by its direction changing or magnitude changing. Okay, so here was a case where I showed you only the magnitude was changing and not the direction. And now I'm showing you the other extreme case. The other extreme case being the magnitude is not changing, but the direction is changing. Okay? In this case, the acceleration, as you learned, is pointing toward the center. So the acceleration is always pointing toward the center. Okay? We mentioned this, and we'll give you the formula for that in a second. So the magnitude of the centripetal acceleration is v squared by r. Is this acceleration constant? The speed is not changing. The radius of the circle is not changing. Is this acceleration constant?
Yes.
Okay. What is an acceleration? It's a vector. The magnitude of the acceleration is not changing, but its direction is changing. So the acceleration is also constantly changing. Okay. What happened to my diagram? Okay. All right. So here's the deal. So when the magnitude of the velocity changes, the acceleration is tangent to the path. So if your speed is changing, you have an acceleration that is tangent to the path. Okay? I'm throwing a lot of information at you. Okay? When the direction of the velocity is changing, you have an acceleration that is perpendicular to the path. Okay? So you can have acceleration when your speed changes, and you can have an acceleration when the direction of your velocity changes. Okay? All right, so now let's apply that. Okay. So here's the path you're going in. Okay. Yeah. So let's say you're going on a curved path like this. Okay. If you have a tangential acceleration, what does that mean? Your speed is changing. Anytime you have an acceleration, your velocity is changing. Okay, velocity is a vector, so I think a lot of confusion is arising because velocity is different from speed. Okay. So if you have a tangential acceleration, that means the magnitude of the velocity is changing. So you can go on a curved path, and if your speed is constant, this component of the acceleration will be 0. Yeah. Now, if you're going on a curved path, the direction of your velocity is changing, so you will have a perpendicular acceleration, or this is called the centripetal acceleration. This is an acceleration that arises because of the velocity changes direction. Okay. Here's a case, your velocity, your speed is not changing and your direction is not changing, and your acceleration is 0. Okay. All right, so that covers all the different accelerations you'll see. Okay, so on a curved path, again, let me tell you, this tangential acceleration is due to your speed changing. And this centripetal acceleration, by the way, this diagram it's slightly off. I'm sorry?
It's not.
Okay. So on a curved path, generally, if you have the tangential acceleration arises from your speed changing, and your centripetal acceleration is because of the direction of the velocity changing. Okay. All right. So anyway, your instantaneous acceleration is dv by dt, which is dvx by dt. Here's your instantaneous acceleration. All right. Before we go on to the next topic, yeah. So let me review what we did. Okay, so what we were interested in was describing a general 3D motion. Okay, so if you wanted to describe a motion like this, what is it that you need to give me? You need to give me your position as a function of time. Okay, once I have that function, I can calculate my velocity, which is dr by dt. And I can calculate my acceleration, which is dv by dt, or the second time derivative of your position vector. Okay. And here was an example. So if somebody gave you this motion, okay, time derivative of that was the velocity, derivative of that was the velocity, and derivative of velocity was the acceleration. Okay. So that's all we've done so far. Okay. Somebody described a motion to you, and we learned how to calculate the velocity and your acceleration. Okay. So we started off by doing a general 3D motion, and now we're going to specialize to a two-dimensional motion. Okay. Why is that? Okay, so you encounter this motion quite a bit, a two-dimensional motion. So for instance, when you throw a ball, okay, we'll consider motion where the only force acting on the object is the force of gravity. So the acceleration will be in this direction, okay, and the object will move in the xy plane, or you can do yz plane or whatever. Okay, so the object will move in a plane; it won't move in the third dimension. Okay, or actually, let me do it this way: xz plane. Yeah. All right, that's fine. So anyway, it will move in a plane. Okay, so that's what we're interested in. Okay, so let's look at a 2D motion now. So now we'll look at a projectile motion. The phrase projectile motion, this refers to an object moving only under the influence of gravity, okay, and where all other forces are negligible. Okay, so for instance, if I throw a ball up and down, or this keychain of mine, this is a projectile motion. Okay. So gravity is the predominant force here. There is a little air resistance, but it's negligible. Okay. For this guy, if I toss a paper, see, that motion is very different than this motion. Why was that motion very different? Is gravity not acting on it? I'm sorry? Yeah, so other forces are comparable to the gravitational force. Lift, drag, and all those forces are comparable to the force of gravity. Okay, so when we do a new topic, what is it that we do? We keep it as simple as possible. So now we want to study a motion, and we'll study a motion where only one force is involved. Okay. If you try to study this motion, okay, what was the difference between these two guys? In this guy, only one force was involved. And that force was constant throughout the motion. Here, for this guy, several forces are involved. Only one force was constant throughout the motion. The lift and drag were changing. Okay? So for $300, we don't want to deal with that. Okay? And so we'll look at projectile motion. Yeah. And what we're going to show you is that this trajectory is a parabola. Okay? So here's the x coordinate of the object, and here's the y coordinate of the object. Okay, and let me show you a couple of things about this projectile motion. Okay, so let's all right, so when you shoot an object, when you throw an object, and if gravity is the only force acting on it, meaning air resistance is negligible and so on, then its trajectory will be a parabola. We'll show that to you. Okay. Now let's look at the velocity vector. Okay, so all right, so what I want you to do is okay, so before I fire that, which way is the gravitational force acting? Downwards. Okay, so here's the acceleration, and the acceleration vector. Okay, so I'm sorry? Yeah. Why do you think that is happening?
It almost looks like it's happening when you're changing between tabs, going from the slideshow back to this.
Mm.
It seems like that's when it's consistently happening, but I'm not quite sure why that is.
So it must be an iPad. It must be, maybe I don't have my because it's happening in all the rooms, and it didn't used to happen last semester.
Maybe it needs an upgrade.
Yeah.
It will make us augmented.
What's that?
Very nice.
All right. So this is 0I minus GJ. Okay. So this acceleration has no x component, and there's the y component of the acceleration. All right, let me remind you of kinematic equations that you saw before. So x minus x naught equal to v naught x plus 1/2 v naught x t. So these are equations that you saw last chapter 1, ax t squared. What is this telling you? This is the x displacement, or it's giving you the x coordinate as a function of time. Okay. So for this motion, there's no x component of the acceleration. Okay. So the displacement changes linearly with time. Vx equal to v naught x plus ax t. Okay. This is the velocity, x component of the velocity as a function of time. Okay. What is ax? 0. So for this motion, what it's saying is the x component of the velocity at any instant is equal to the initial x component of the velocity. So the velocity is tangent to the path, but the x component remains constant. So similarly, y minus y naught equal to v naught yt plus 1/2 ayt squared. Ay is not 0. Ay is minus g. Okay, so the y component is a quadratic function of time. Vy equal to v naught y plus ayt. Okay, the y component of the velocity will change with time. The x component of the velocity will not change with time. Okay, so that's what I want you to notice. All right, so what we're going to show is we're going to show the velocity vectors, we're going to show you the components, and you know that it's going to be a parabolic trajectory. And so watch the x component of the velocity, you see it's not changing. The y component of the velocity was changing. Okay, so I'm going to do it again. All right. So the horizontal component of the velocity is the x component of the velocity. The vertical component of the velocity is the y component of the velocity. Okay, and initially the y component of the velocity was like that, but the acceleration is pointing in downward, so it's changing in the downward direction. Okay. Okay. So at any given instant, the velocity vector is tangent to the path. At the top, it's tangent to the path. So what is the y component of the velocity at the top? 0. Very good. Okay. So that's the apex of the trajectory. Okay. At the top, the y component of, how do you know you've reached the top? Your y component of the velocity is gone 0. Okay. All right. Everybody understand that? Okay, so this is what we're going to talk about in the next few slides. All right, and that's what's shown here in this diagram. See, so again, here's the initial velocity. That's the launch angle theta naught. Here's the x component of the velocity, and you see it's constant. Okay, it's not changing. It's the y component of the velocity that's changing. Okay. So when we say we're talking about projectile motion, it's only relevant force is gravity. Okay. Air resistance is negligible. The horizontal and vertical components are independent of each other. What that means is, okay, motion in the x direction is not influenced by forces in the y direction. Okay, so in mutually orthogonal directions, motions are independent. Okay, so for instance, if I attach a rocket to this guy in this direction, this motion is unaffected by the rocket. All right, so so here's an example, and go home and think about this. All right, so what I'm going to do is I'm going to roll this chalk off the table. Okay, the faster it comes off the table, the further it'll fall, right? But when it's coming off the table, does it have a vertical component of velocity? I'm sorry? That's right. Okay, so at the instant it comes off the table, the velocity is horizontal velocity. Okay. So now you have to picture this. This is coming off the table, and I'm going to drop this chalk. Which one hits the floor first? They hit at the same time. Okay. Their y component of the velocity is the same because they didn't have any initial y component of the velocity.
Is that just universal, that the different components will never affect each other?
That's right.
Okay, so if you're in orthogonal directions, the motions are independent of each other. Okay, so the horizontal and vertical motions are independent of each other. Okay? The trajectory of such a projectile is a parabola. Okay, and Elon, they launch a rocket, and they know exactly where to catch it. This is why they know exactly where to catch it. Okay. All right, so this goes through the derivation, showing you that it's the trajectory is a parabola. Okay, so here's the y coordinate, here's the x coordinate. What is the equation for a parabola? It's a quadratic. If x and y are related like so, then the trajectory is the curve is a parabola. If a is negative, the parabola it opens downward. Okay, so you've learned this from your calculus classes. Now let's show that this is true. Okay. So you saw that for an object moving only under the influence of gravity, the acceleration is 0I minus gj. Okay, so x minus x naught equal to v naught. So for this object, here was the initial speed, there was the launch angle. Okay, v naught xt plus 1/2 ax t squared. Okay, and we'll say it starts off at the origin, so x naught is 0. So this guy is 0. Ax is 0. The x component of the acceleration is 0. So the x coordinate of this object is after time t is given by that. Okay. So after time t, if the object is there, the x coordinate, this is given by this formula. Okay. That's what that is. Let's look at the y coordinate of the object. Y minus y naught equal to v naught y t plus 1/2 a y t squared. Okay. We've started at the origin, so y naught is 0. Okay. This time ay is not 0. Ay is that. Okay. So y was equal to v naught y, which is v naught sine theta naught. This is the initial component of the velocity. Here's v naught x, here's v naught y. Okay. Times t minus 1/2 gt squared. Okay. What we're going to do is solve for t from here. T is x divided by v naught cosine theta naught. And we're going to plug it in here. So y is v naught sine theta naught. T is x over v naught cosine theta naught minus 1/2 g x square v naught square cosine square. So you see y is a quadratic function of the x coordinate. Okay, so if you're on this trajectory, your y coordinate is a quadratic function of the x coordinate. And you see the coefficient is negative. Okay, so this trajectory is a parabola. As long as the y coordinate is a quadratic function of x, you know that that's a parabola. So what we are saying is, if you have a constant force, okay, it doesn't have to be gravity, it can be any constant force. Okay, if you're traveling under that constant force, Your trajectory is a parabola. All right, let's say I shoot an intercontinental ballistic missile. Will that be a parabolic trajectory? This changes over if you go fairly high up. Okay, yep. But I mean, it won't change a whole lot. Yep.
So I understand from the x component that when we cross out the x, it's because it's just zero, so it cancels out, that doesn't part of the equation.
Mm-hmm.
Why are we crossing out the y term and the y that doesn't make the rest go?
Okay,
Well,
this,
y plus u, right?
you start at the origin,
Yeah.
so x naught, that's the coordinate, your x coordinate at time zero. This is a y coordinate at time zero. Those two are zeros. This guy, there's no x component to the acceleration. That's why this is a zero. Ay is minus g. And then here was y as a function of time. And what we did was solve for t here and then put that in there. Okay. All right, so what we have shown you is that this is a parabolic trajectory. As long as you, when will you have a parabolic trajectory? As long as you have a constant force acting on it. Okay. And there will be many situations when you will have parabolic trajectory. I mean, the most common is, of course, projectile motion. The range is the horizontal distance you have traveled when you come to the same vertical position. Okay, so you can range, it doesn't have to be from ground level. You can throw the ball from the top of a building. You could use the range formula for this distance. Okay. As long as you've come to the same vertical position, that's the horizontal distance traveled. Okay, so the range is v naught square, your speed square, times sine 2 theta. Theta naught is the launch angle, divided by g, the acceleration due to gravity. Okay, when do you get the maximum range? At what launch angle do you get the maximum range?
45 degrees.
Yeah, 45 degrees. So you're just maximizing this value, and that's, okay, everything else being constant, okay, this, the maximum value of this is 1, and sine 90 is 1, so that makes that 45 degrees. All right, so a launch angle of 45 degrees gives you the maximum range. Okay. What launch angle gives you the maximum height? 90 degrees, of course. Okay, so here is the height, vertical height travel, and that's equal to v naught square sine square theta. Okay, so when theta is 90, that's 1, and sine square 1 is, 1 square is 1. Yep.
Why is the first equation set to 0?
Oh, the range of the projectile. So this is your y naught. This is your final y. Y minus y naught. You come to the same vertical location.
Oh, okay, sure.
So these are the range and height formulas. Okay. Many of you may or may not know this. So here is the range. Again, this is projectile motion with air resistance negligible. And look at this, notice this. The range is the same for 15 degrees and 75 degrees. It's the same for 30 degrees and 60 degrees. What do you notice? Can you say anything about that? For complementary angles, the range is the same. Okay, so these are complementary angles. And of course, 45 degrees is complement to itself, so the range is the same. Okay. Okay, so here's a parabolic trajectory. Here's another parabolic trajectory. Here's the trajectory of a real baseball or a tennis ball, let's say. So what can you tell me about these guys? They're very good. Very good. Okay. So for these guys, okay, gravity is not the only force. Okay. The other forces are comparable to the gravitational force. Okay. So this is what happens when you put a top spin. Okay, and if you watched tennis yesterday, so yeah, the more top spin you put, the more it'll fall closer to there. Okay, so the harder you hit and the more top spin you put, the less chances are for it to go out. Okay. All right. I have 7 more slides. Do I finish the lecture, or do you want a break? I'd rather. Are you guys? Anybody tired? No. Finish the lecture. Okay. All right. That's good. Okay. So now we'll consider uniform circular motion. Okay. So you're going in a circle, and the uniform refers to your speed is uniform, meaning constant. Okay, so you're going to drive around in a circle at constant speed. So this is showing you your velocity vector. Okay, and as we keep saying, your velocity vector is changing even though its magnitude is not changing. Okay, so for this case, for this velocity, what is changing? The direction is changing. Okay, and when only the direction changes, then your acceleration is perpendicular to the path. Okay, when only the direction of the velocity changes, the acceleration is perpendicular to the path. And in fact, if this was the curve and if you completed the circle, you'll find that the acceleration points towards the center of the circle. So it's also called a centripetal acceleration. Okay? So the name is descriptive. The acceleration points to the center. And since as the position of the particle changes, the direction of the acceleration is changing. Okay? So the acceleration is not constant. But it turns out that the magnitude of the acceleration is constant, and it's given by that. It's your speed square divided by r, the radius of the circle. Okay. So, for instance, we talked about this. So here's the sun, here's the earth. The earth is going at a constant speed of 30 kilometers per second. Okay, its speed is not changing, but the direction, the velocity of the curve, the earth direction is changing, and the earth has a centripetal acceleration given by that. Mr. Newton tells us that anytime you have an acceleration, you have to have a force acting on you. And what is that force that's making the earth go around the sun? Yeah, the gravitational force. Okay, so that centripetal force has to equal the gravitational force. This could be the earth, and so this could be the earth, and this could be a satellite going around the earth. And all those satellites go around at constant speed, and it's the Earth's gravitational force that is providing the centripetal force. Okay? So in a lot of our problems, what we'll do is we'll look at an object's motion, we'll we'll know whether it's accelerating or not. And if it's accelerating, then we go look for the source of the force. Okay. All right. So for this car going around in a circle like this, so
You can see it.
all right, what's your name?
Ava?
Ava. I need a solution by Wednesday. All right. So here's a car going around in a circle. Okay. You saw that the centripetal acceleration is pointing in this direction. You need a force. Where is that force coming from? In this case. I'm sorry? The car's engine pushes this way. I'm sorry? The static friction force. You'll see that it's a static friction force. It's static friction force because the car is not moving in this direction. Very good. Okay? So it's a static friction force. Let's say, so if there was no friction, so for instance, if you were, okay, I don't know if, at least you've seen this on TV. Let's say you're on skates, you're skating on ice. If you're vertical, you can't turn. To make a turn, you have to have your skates at an angle so you can have a centripetal force. So, if you didn't have any friction, you couldn't go in a circle. If you were a plane, so let's say so all right, I guess I'm recording this, but I can't do a drawing like that. All right, so here's a plane that's flying. The lift is in this direction, in the upward direction. So when it's in level flight, the lift is balancing the weight and it's not falling into the sky. But if you want to turn, if you want the plane to turn in this direction, what do you have to do? You have to tilt it. Why did you have to tilt it? Now the lift is in this direction, and this component of the lift is providing the centripetal force. This component of the lift is keeping you from falling down. Okay. So that's a good example. All right. Okay, so the centripetal acceleration will show you that the centripetal magnitude of the centripetal acceleration is that. Okay, so anytime you're going in a circular path, you need that much acceleration, and then again, like I said, in problems, we look for the sources of the force. Okay. In planetary motion, it's the gravitational force that is providing the force. Okay. You guys probably all know this. So we live in the Milky Way galaxy, and the sun is going around in a circle like that. And it takes us 200 million years to go around. To complete one orbit. Okay, and we are going at constant speed, so the entire solar system is going at constant speed. What is providing the centripetal force? I'm sorry?
Still gravity?
It's gravity. It's the gravitational force of all these stars, all the mass contained within that circle. Okay. All right, so again, like I said, if something is accelerating, we go look for the sources of the force that are causing the acceleration. Okay, so now let's look at this guy. So we're looking at this guy traveling in a circle. The speed is constant, so that's the magnitude of the velocity is constant. So let's say that's where the particle is located now at an angle theta. R is not changing, R the radius of the circle, okay? Okay, the velocity is, so if this angle is theta, the velocity is tangent to the trajectory, so this angle will be theta, okay? These two guys are perpendicular to each other, okay? Here's the x component of the velocity, here's the y component of the velocity. There's the x coordinate, y coordinate. X component of the velocity is, so the velocity is Vxi plus Vyj. The x component of the velocity is negative V sine theta plus V cosine theta j. Okay, so this side of the triangle is V sine theta, and I put in the negative sign by hand because it's pointing in the negative x direction. Okay? And the y component of the velocity is this side of the triangle, which is V cosine theta. Okay? Now let's look at this triangle. We'll write cosine and sine theta in terms of the x and y coordinates. Okay, so sine theta is y divided by r. Sine theta is y divided by r. Cosine theta is x divided by r. Okay, what we're going to show you is the magnitude of the acceleration is that. The magnitude of the centripetal acceleration is that. Okay, once you have the velocity, if you want to calculate the acceleration, what is it that you do? Take the time derivative. Acceleration is time derivative of velocity. Your speed is constant. The radius is constant. So when you take the time derivative, all you're doing is only this is changing. Only the x and y coordinate of the particle are changing. Okay, so it's dy by dt, which is vy. Dx by dt is vx. Okay, so acceleration is that. V and r are constant. And vy, again, we saw that vy is v cosine theta, and vx is v sine theta. Okay, so here is the acceleration, and the acceleration is a function of time. Because why is that a function of time? Because as you're going around, theta is a function of time. But the magnitude of the acceleration is ax squared, ay squared, this square times this square, which is v squared by r. And the magnitude of the acceleration is constant. Okay, now what we're going to show you is that the acceleration is pointing towards the center. Okay, so when the particle is here, again, theta, okay, so we'll look at it for an acute angle, theta. When theta is acute, let's look at this expression. V squared is positive, r is positive, cosine theta is positive, sine theta is positive. So these guys are positive. But you can see these negative signs. Acceleration, when the particle is in the first quadrant, the acceleration vector is in the third quadrant. Yep. So the acceleration vector is in the third quadrant, and let's call this angle phi. Okay, tan phi is ay over ax, which is that over that, which is equal to tan theta. So, and you guys know that tan theta is equal to tan theta plus 180 degrees. Okay, so phi is theta plus 180 degrees. So the acceleration vector is pointing towards the center of the circle. Okay, that's what this shows you. Okay. Anyway, so there's the magnitude of the acceleration, and the direction of the acceleration, it's towards the center of the circle. All right. So this is tangential and radial acceleration. Okay, so when you go on a general trajectory, you have tangential acceleration. When do you have tangential acceleration? I'm sorry? You get a soda if you answer it right, maybe. When do you have tangential acceleration? Very good. When your speed changes, when the magnitude of the velocity changes. Okay, so you'll have tangential acceleration when your speed changes. So you can go on a curved road, and if your speed is not changing, this tangential acceleration will be zero. When do you have a radial acceleration? When your direction changes. So when you're going on the curved portion, that's when you'll have radial acceleration. When you're going on a straightaway, you won't have any radial acceleration. Okay, your speed can change all at once. Okay, but when you're going on a straight road, you don't have radial acceleration. Okay, so here the speed is changing. Here you have radial acceleration because the path is curved, and there's your total acceleration. Okay, so assuming this is the direction you're going, you're speeding up. What if you were slowing down at this point? Which way would your tangential acceleration point? In that direction, and your total acceleration would point to this. All right, I'm going to sort of quickly go over the slide here. Now, what we want to do is the following. We want to study relative motion. Okay, again, the bigger goal is the following. So here's this person driving, here you're driving, here's another person driving, and there's a third person. Okay. What does this guy see? How fast is this person moving relative to them? They're not. They're at standstill. And relative to them, this person is moving at 60 miles an hour. All right, so one of the things is the following. So let's say this dog was juggling inside the car. Okay. When the dog tosses a ball, what is the trajectory of the ball? I'm sorry? It's a parabola. Okay? So if the dog tosses a ball, it's a parabolic trajectory. What does this person see? I'm sorry?
Ball going out, it's going right back down.
No, okay, so those two cars are not moving relatively to each other. So I see a parabola, you see the exact same parabola. Okay, this dog is tossing this ball, and that's the parabola. This guy will see the exact same parabola because they don't have any relative motion. What does this lady see? This lady will see a wider parabola, but she'll still see a parabola. Okay? All that happened was, see, when the dog tossed the ball, there was the x component of the velocity, but what the lady was seeing is a larger x component of the velocity, and so the parabola is wider. But she still sees a parabola. Okay. Now, if the lady sees a parabola, what does that mean? When do you get a parabolic trajectory?
What is your force, I guess?
The force is constant. The force is the same. Okay. So if you're moving relative to each other at constant velocity, the forces that you see will be the same. Okay. All right, so anyway, that's what we want to describe, and so we'll show you a little mathematics related to it. Okay, so here's one frame of reference, so this will be this frame of reference, and that's the particle that is moving. So in one frame of reference, there's the particle that is moving, and here's the other frame of reference, and she is watching this particle moving as well. Okay. So if the location of this particle with reference to this frame is that, and this frame is moving with reference to that, so there's the location of blue car, and there's the location of the red car with reference to the blue car. Okay, so here's the particle. Okay, here's the position of the particle with reference to the S prime frame. Here's the position of the S prime frame with respect to the S frame. Okay, position of the S prime frame with respect to the S frame. Okay. Again, the notation seems complicated. You don't have to remember all of this. I'll tell you what formula you have to remember and how to remember it. So here is the particle located with reference to one frame, and here is the same particle with reference to the other frame. Okay. So RPA, position of particle with reference to frame A. RPB, position of particle with reference to frame B. And here's frame B with respect to frame A. Okay. So here's how you remember this. Position of particle with reference to frame A. Position of particle with reference to frame A is position of particle with reference to frame B plus position of frame B with reference to A. So you can see that you gotten this by just inserting B in between these two. You inserted B, RPB, and RBA. Okay. Anyway, RPA is RBA plus RPB. Here is the position, and as this position changes, if this is a position with respect to time, all these guys will be functions of time. You want to calculate the velocity, just take time derivative of that. VPA equal to VPB, VBA. You want the accelerations, you take the derivative of the velocities. Okay. And as long as frame B is not accelerating, with respect to frame A, if it's moving at constant velocity, this will be 0. Whatever acceleration frame A sees is what frame B sees. So if two frames are not accelerating relative to each other, they see the same accelerations. They see the same forces. Okay, so that's the important thing. Okay. So for instance, here's something that you encountered. Let's say it's raining straight down in the ground frame of reference. And if you're driving, how do you see the rain falling? Okay. So the velocity of the rain with reference to the car is equal to velocity of the rain with reference to ground. Remember, you can insert a letter. Okay. Velocity of something with reference to another thing is equal to velocity of that thing with reference to another frame plus VBA. Okay. So velocity of the rain with respect to car is equal to velocity of rain with respect to ground plus velocity of ground with respect to car. Here's the velocity of the car with respect to the ground. So what is the velocity of ground with respect to car? It's in the opposite direction. The ground is moving in the opposite direction. Okay. All right, so the velocity of rain with respect to the ground is that. Velocity of the ground with respect to the car is like that. And so the velocity of the rain in the car is in this direction. Okay, and that's what you'll see. Okay. All right, so so this kind of stuff is useful when, for instance, let's say you're flying and you want to go from here to there, and the wind is blowing in this direction. Okay, so you can't fly straight at that direction because you'll end up there. Okay? So you have to fly in this direction so the wind blows you over that direction. Okay? Now, this can be significant because let's say you're flying a plane that's flying at 500 miles an hour, and if the wind is blowing at 50 miles an hour, which is 10%, so you'll have to account for that. Okay, and people have to do that all the time. Okay. And now the situation is, let's say a river is flowing and you want to cross the river. Okay. If the speed of the river is non-negligible, okay, you have to flow up. You got to, you got to drive upriver to end up across the river. Okay. All right, guys.